Thank you all for attending this final applied PDE seminar of the spring quarter here at the University of Washington. We are working on lining up an exciting slate of applied PDE seminars for next academic year. Even though we will be back on campus in the fall, this PDE seminar will continue online as it has been for the past 5 years. Today's speaker is David Goluskin from the University of Victoria. David works on different aspects of nonlinear dynamics, a lot of times in fluid dynamics. David did his PhD at the University of Columbia University under the direction of David Keyes, after which he was a postdoctoral fellow at the University of Michigan before moving to Victoria. So thank you, David, for giving today's talk.
Great, thank you. I'd like to talk today about how different kinds of variational problems arise when trying to study fluid equations, and how the effort to generalize classic methods of analyzing these equations lead to harder variational problems that are generally intractable. But one way to approach relaxations of these harder variational problems is to use relatively recent tools from computational optimization. So I'm hopefully going to make it to both halves of this talk. First, I'm going to describe how one can try to derive results about nonlinear stability of particular fluid flows. And then I'm going to describe how one can derive bounds on infinite time averages of quantities of interest. Methodologically, these two halves are extremely similar, which is why I'm going to try to cover both of them. In the case of nonlinear stability, essentially all global stability results in fluid dynamics have been derived in the same way for over 100 years, using a relatively simple approach called the energy method. And this leads to variational problems, in particular quadratic integral variational problems that can be solved using standard methods from the calculus of variations. On the other hand, the results that one gets from this approach are often overly conservative. You'd like to get stronger results. So the question is, mathematically, how do you generalize this approach? As I'll describe, this leads to much harder variational problems. I will describe one possible way to confront these. And I'll show you an example for an application to coetflow, which is one of the canonical models of fluid dynamics. For bounding time averages a priori, well, here it's a very similar mathematical approach, which in this case in the literature goes by the name the background method, but which once again leads you to quadratic integral variational problems. So again, the question of how to generalize leads you to harder variational problems, and I will describe an application, in this case, to the 1D Kuramoto-Sivashinsky equation, which has the same kind of nonlinearity as Navier-Stokes. So let me just jump right in to how you could try to figure out nonlinear stability of a solution to the Navier-Stokes equations. So what I will call the laminar state, this vector field capital U, this is just a time-independent solution to Navier-Stokes whose stability you're interested in. So if you consider, for instance, fluid flowing through a straight pipe in parallel lines, right, there's a simple laminar solution to the Navier-Stokes equations, and you might ask whether perturbations to that laminar state will grow or decay. So perturbations in particular, I'm going to denote this vector field as lowercase u. And according to the Navier-Stokes equations, lowercase u for incompressible fluids will evolve as I've written here. I've written this in dimensionless form, so there's a single dimensionless parameter in the system, which is this Reynolds number Re. When the Reynolds number gets large, right, then the coefficient in front of the dissipation gets small, and this is when we expect to have strongly turbulent flows. So as the Reynolds number goes to infinity, you have more and more complicated nonlinear higher dimensional attractors. You'll have generally turbulent activity over a wider range of spatial scales. On the other hand, when the Reynolds number is quite small, the laminar state will be globally attracting. All perturbations will monotonically decay. All right, so there's some threshold Reynolds number in the middle at which the laminar state ceases to be globally attracting. What that exact value is depends on the particular fluid configuration that I'm talking about. So a classical question in fluid dynamics is, for what Reynolds number is at the laminar state, where the perturbation vector field is 0, globally attracting in, generally you would ask this in the sense of the L2 norm. So for what Reynolds numbers do all admissible perturbations eventually have an L2 norm that goes to 0, not necessarily monotonically as time goes to infinity. Right, so you know, typically in a time-dependent ODE or PDE, if you want to show that a particular solution is globally attracting, you try to construct a Lyapunov function or functional. So just to be sort of generic, let's assume that at all instants in time, our perturbation field is in some space of spatial functions, which I can denote as script U. And there's various flavors of what conditions I would want a Lyapunov functional to obey, but here's one possibility. Suppose there exists a functional V, right? This is a real valued functional that its input is some vector field that's a function of space, not explicitly a function of time, and it spits out a real number. And suppose you can show that V is strictly positive except for the 0 vector field at which it's 0. So V has a minimum at the 0 vector field, and it obeys, well, V is not explicitly a function of time, but if you consider evaluating it along PDE solutions, right, then you can take the time derivative of V, and suppose it obeys this differential inequality, right? It's bounded above by some negative constant times V, right? Then by some kind of Gronwall type argument, you can say that V goes to 0, right, as time goes to infinity. And then this will imply for any norm that's controlled by V that that norm of perturbations also goes to 0. In other words, the laminar state is globally attracting in the sense of this norm. The question then is, what functional V should you choose to try to show that it goes to 0 as time goes to infinity? Well, in the history of fluid dynamics, this has been done essentially in one and only one way. There are slight variations on this depending on the details of the system, but the only thing that works in general is the so-called energy method, where the Lyapunov functional that you choose is just the L2 energy of perturbations of the velocity vector field. Right? This goes back to Reynolds in the late 1800s or in 1907. Right, well, first of all, this is strictly positive when U is non-zero, so that condition is trivially satisfied. So then the only thing we have to figure out is, when can we say that for all admissible perturbation vector fields U, that V is monotonically decreasing in time? All right, well, if we take the time derivative of V along solutions of the PDE, and if we, if things are nicely behaved and we can put the time derivative inside the spatial integral, right, then we just replace that with the right-hand side of the Navier-Stokes equations. And for typical boundary conditions, various terms in this integral vanish. In particular, the pressure vanishes, which is convenient. U dot grad P vanishes. That's not necessary, but it's convenient. But what is completely essential for this to work is that the cubic term vanishes. Right? This term that has 3 U vectors in it, that term vanishes. And if I integrate by parts, right, I now just have a quadratic integral. The first term is negative definite, and the next term is not sign definite. So then the question becomes, for what Reynolds numbers does the first term dominate the second term? And I can say that this time evolution of V is less than or equal to 0. Now notice here, there's no explicit time dependence anymore. So I can just regard this as another functional of spatial functions. I can call it LV if I like. This would stand for the lead derivative of V along solutions of the PDE, if you want. And in the present case, let me just multiply and divide by V, right? So I can say that I have this functional f of U multiplied by V. And of course, f of U is bounded above by its maximum value among all admissible spatial functions. And this is where a variational problem comes into the analysis. Right? So if I could solve this variational problem where I maximize the functional f, and I call that maximum lambda 1, which depends on the Reynolds number. And if I can solve that variational problem and verify that lambda 1 is negative, then V is indeed a Lyapunov functional, the energy is a Lyapunov functional at a certain Reynolds number, and therefore the laminar state in this fluid flow is globally attracting. But this functional f of u is a ratio of two quadratic integrals. So this is a problem that's solvable by classic methods in the calculus of variations. The minimum is attained. You can write down the Euler-Lagrange equations. They are linear. And what you end up with is simply the eigenproblem for the energy stability operator. So notice that the Reynolds number enters as a parameter. There will be some spectrum of eigenvalues lambda. They're all real. The operator here is symmetric. So all the lambdas are real, and I want to know if the maximum one, which I've called lambda 1, is less than or equal to 0. Right? And if it is at a particular Reynolds number, then I conclude that for all admissible perturbations, the energy decays monotonically. Therefore, the laminar state is globally attracting. Okay? And in particular, what will happen is this will be true up to some finite Reynolds number, above which it ceases to be true. And this is the energy stability Reynolds number, right? The largest Reynolds number such that the maximum eigenvalue of the energy stability operator is not positive. I guess I should confirm that you can all hear me and I'm not having any internet problems. Everything good so far? Great. Now I'd like to point out a few things about this classic method of analysis. The first is that whatever threshold Reynolds number you get is a linear property, right? Whatever this threshold is exactly the same for the linearized Navier-Stokes equations, right? The nonlinearity of Navier-Stokes vanished from this integral, right? So essentially, we are able to prove that the laminar state of the nonlinear Navier-Stokes equations is globally attracting exactly for those Reynolds numbers where there is no transient growth of energy in the linearized Navier-Stokes equations. But this is restrictive because the linear operator is highly non-normal, more so as the Reynolds number increases, so transient growth of energy is the typical situation. So this has no way of capturing the fact that there could be transient growth that saturates due to the presence of the nonlinearity. So there's no way for the nonlinearity to help you here. Right. On the other hand, the nonlinearity has hurt us in the sense that energy, the L2 energy, is the only quadratic Lyapunov functional that we could possibly try to use. The reason being, I needed this cubic term to vanish. Right? If this cubic term hadn't vanished, then the maximum of the f functional would be plus infinity, and this analysis would never succeed, right? So in other words, I needed energy to be conserved by the nonlinearity of Navier-Stokes. Another way to say that is I needed energy to be an invariant of the Euler equations, which it is. Now, there are a few other quadratic invariants of the Euler equations, but none of them work for reasons I won't go into. So basically, energy is the only quadratic Lyapunov functional you can use due to the constraints of the nonlinearity, and yet the nonlinearity doesn't help you in the ultimate analysis. On the plus side, because I've picked a quadratic functional, the variational problem was tractable by standard methods. However, what you get out of this analysis tends to be pretty conservative. As an example in this talk, I'm going to use coetflow, which is one of the classic examples of fluid dynamics. Here you have a layer of fluid. It's confined between two boundaries that are moving parallel relative to each other. So the simplest time-independent solution to the Navier-Stokes equations will be a linear shear profile, like the one that's drawn here. Then the question is, at what Reynolds numbers is this linear shear profile globally attracting against all admissible perturbations of the velocity field? Well, the energy eigenproblem is relatively simple here because the tensor that I've boxed is just this constant value. And you can solve this semi-analytically up to doing a little bit of linear algebra on a computer. And if I, for example, fix the Reynolds number to the arbitrary value of 240, and I fix a domain whose width is twice its height, and I consider perturbations that are horizontally periodic, but that are bounded by solid boundaries on the top and bottom, right? Now this is a bounded domain, so I have a discrete spectrum of eigenvalues lambda and associated eigenmodes. And these leading eigenmodes are what I've drawn on the right-hand side here. These first guys in the upper left are horizontally uniform. And the other ones, what I'm showing is the streamlines of the fluid. So there are eigenfunctions, and these lines are the lines that the fluid particles would follow as the fluid flows. Each one of these has an associated eigenvalue. If you look at the plot here on the left, ignore the colors and the curves, just look at the black dots, right? For various admissible horizontal wave numbers that fit within the domain, right, we have different black dots, and at least one of them has a eigenvalue lambda that's positive. What this means is that the energy for perturbations in this eigenmode will grow at this Reynolds number. So this is not an energy stable Reynolds number, and I cannot conclude using the energy as a Lyapunov functional that the laminar state is globally attracting at a Reynolds number of 240. But what you can do is you can search for the maximum Reynolds number for which all eigenvalues are non-positive, and you get a threshold value of about 177, and this is what Orr found a long time ago in 1907. But this value of 177 is not a sharp answer. In fact, for all the sort of classic fluid models in which you have a base state where the fluid is running parallel, your answer from the energy stability method is not sharp. So the situation tends to be the following. This is true for coetflow, for flow through a pipe. The transition to turbulence is subcritical, which is why it has been quite hard to understand until very recently to come up with a reasonable theory of the transition to turbulence in such situations. I'm going to draw you a sort of bifurcation diagram cartoon, where on the vertical axis I have the norm of the perturbation from the laminar state. So for that, on the laminar state, of course, that norm is 0 for all Reynolds numbers. And then at a certain Reynolds number, there comes into existence a chaotic attractor, which as the Reynolds number increases farther and farther, you would begin to call turbulence. The laminar state, in many of these cases, remains locally attracting, but not globally. But at smaller Reynolds numbers, there come into existence unstable nonlinear states, traveling waves, periodic orbits. Depending on the particular configuration, these may or may not connect to the laminar state in a linear instability. Right? And what I'm asking about in the first half of this talk is, what is this Reynolds number, which you could call the smallest Reynolds number at which nonlinear states exist, or you could call it the largest Reynolds number at which the laminar state is globally attracting. Right? Now, classically, we don't know this number. All we get is the energy stability Reynolds number, which is smaller, often much smaller, which gives us a lower bound on the true global stability cutoff. For example, flow through a straight pipe, which is one of the most classic examples in fluid dynamics, all we can say is that this global stability threshold is somewhere between 81 and 773, right? So this is a rather crude estimate. 773, because at that Reynolds number, particular traveling wave solutions have been computed numerically. 81, because at below that Reynolds number, the energy is a valid Lyapunov functional. But in between there, transient growth of energy is possible, and no other Lyapunov functional has ever been constructed for technical reasons. So the question is, how can we do better? In this talk, I'm going to use this even simpler example of 2D Couette flow, where you have the energy being a valid Lyapunov functional only up to a Reynolds number of 177. Above this, nothing is known. No nonlinear states have ever been found. It's quite likely that the laminar state is actually globally attracting at all Reynolds numbers, but in over 100 years, nobody has shown it. All right, so in order to show that the laminar state is globally attracting in the sense of the L2 norm at any larger Reynolds number, we must generalize the Lyapunov approach beyond quadratic integrals, because if you restrict yourself to a quadratic integral for reasons I explained, you have to use the energy, and the energy does not work well, or it doesn't work at all above this Reynolds number. Okay, there are various ways, infinite ways in which one might consider a more general functional than a quadratic integral. I'm going to do one possible thing, which is probably not the only possibility. And to tell you why I did it in this way, let me tell you about the ODE case. So let's just consider an ODE dynamical system. So the state vector A lives in Rn. And in this case, we would be looking for a Lyapunov function V, which is a real valued function on Rn. The time evolution of V along ODE solutions by the chain rule is just f dot grad V, where f is the right-hand side of the dynamical system, right? So this is just some other real valued function on Rn. And well, this is not quite strong enough, but a necessary condition for your Lyapunov function would be that V is non-negative pointwise on Rn, and f dot grad V is non-positive pointwise. Now, in general, there is not a constructive method for finding such a V, but contrary to what you might have learned in school, it is not true that there don't exist constructive methods. In the very important case in which the right-hand side of your dynamical system is polynomial, there do exist constructive methods as of about 15, 20 years ago. In particular, I'm going to search for Lyapunov functions V that also are polynomials on Rn up to some maximum degree. Right? In other words, I'm going to look for a V that lives in the vector space P of polynomials in n variables of maximum degree D. Right? That's a finite dimensional vector space. So you might imagine that this is now a problem that's amenable to computation. I'm searching for a polynomial in a finite dimensional space subject to pointwise inequality constraints. Unfortunately, it turns out this is still too hard because verifying pointwise non-negativity of a multivariable polynomial in general is an NP hard problem. However, you can slightly strengthen these non-negativity conditions to obtain sufficient conditions that are computationally tractable. In particular, I'm going to require V to be in the set that I'm calling sigma n. This is the set of polynomials that admit a sum of squares representation in n variables. Just to be explicit, V being in sigma n mean there exists some finite set of polynomials Q such that if I square them and add them up, I get V. So clearly, if there is a sum of squares representation for V, V is non-negative. Right? And the nice thing is that checking whether a polynomial is sum of squares is computationally tractable. In particular, this is a type of convex optimization problem called the sum of squares program. Now, I say optimization. In this case, there's no optimization objective. So this is what you would call it a feasibility problem. I'm just trying to find at least one member of the constraint set. Right, so I could say specify V in any chosen basis, a finite basis, and the coefficients of V are tunable. And those tunable coefficients appear linearly in both of these expressions. So I have polynomial expressions with linear tunable coefficients, and I'm requiring these expressions to be sum of squares. That is what constitutes a sum of squares program. So a sum of squares program, this has been an area that's become quite active in certain communities over the past 20 years, ever since it was recognized that this can be equivalently translated into a semi-definite program, which is a slightly better studied type of convex optimization problem. If you haven't heard of a semi-definite program, you've probably heard of linear programming. Semi-definite programming is just a different type of conic optimization problem in which your optimization variable is a symmetric matrix and you are constraining it to be positive semi-definite. I won't go into details. I'm just going to say that this type of problem with tunable polynomials and sum of squares constraints is something that a computer can do. Okay, so that's the ODE case. So whether or not you've heard of it before, there is a constructive computational method for finding polynomial Lyapunov functions for an ODE. I want to bring this technology to the PDE case. Therefore, I'm going to try to generalize quadratic functionals in a specific way. Skip that. So In particular, the second simplest thing one could do is look for a cortic Lyapunov functional. And I'm going to constrain the leading term to be the energy squared. This is for the same reason that when you have a quadratic functional, you can only use the energy. Right? Well, you can't have constant and linear terms because v has to have a minimum at 0. But if you are cortic, you suddenly have freedom because you can have other terms. In particular, you can have terms that have cubic or quadratic dependence on u. Now, there's an infinite number of ways in which I could write down functionals that have cubic or quadratic dependence on the u vector, which remember is the unknown perturbation field that I'm trying to show always goes to 0. And I'm going to do this in a very particular way, basically because we knew how to make this work, which is I'm going to follow this idea of Goulart and Chernyshenko, where I'm going to expand u in a partial Galerkin expansion. So I'm going to take n modes from some chosen basis. So these u sub n modes, these are known spatial functions that I've selected, right? But the projections onto this basis, the an amplitudes, these are unknown, right? Because my u is an arbitrary perturbation field. So these are essentially arbitrary amplitudes. But I'm not truncating the system. I am treating the full PDE here. I'm going to retain the tail of this partial Galerkin expansion, and I'm going to give a name to the energy of this tail as q squared. Okay, and then I'm going to do something particular, which is I'm going to say that my cubic and quadratic terms are going to be polynomial in these finite number of projection amplitudes A and the energy of the tail. So V can be considered as a functional of an arbitrary perturbation in the Navier-Stokes equations, but it could also be considered as a polynomial in n+1 variables. Because it's only allowed to depend on the energy of the tail, it can't depend on the tail of U in any more complicated way. Right? In this case, the first requirement of the Lyapunov functional, that V is non-negative everywhere, can be enforced not with any kind of variational problem, but by considering V as a polynomial and requiring that it's representable as a sum of squares in its n+1 variables. Okay, that's pretty easy, right? I just turned a PDE problem into a finite dimensional ODE type thing. But it's not so simple because I also need to consider the time evolution of V, right? And that depends on the full PDE variables. So in particular, I have my polynomial V. If I take the time derivative of V along PDE solutions and I use the chain rule, right, this says that I'm going to need expressions for how these projection amplitudes A vary in time, and also how the energy of the tail varies in time. Now I can get explicit expressions for the time derivatives of A and q squared, right? The A's, these are projections onto modes. So if I just integrate the entire Navier-Stokes equations against a certain mode and project onto that mode, I do get explicit expressions. They're just complicated, but this can be done. So let me just say that the expressions for the time evolution of the A vector, which is finite, and the energy of the tail, take the following form, where if I unwrap all these symbols, I get what's in this box. And we don't really need to look closely at it except to say that this is fully explicit, as long as you can take Laplacians and compute integrals, which you can do semi-analytically with a little bit of help from a computer, that this is a fully known system. So then if I plug in these two equations, expand out this right-hand side, right? I've now written this as a functional, right? This is my LV functional, a functional that has no explicit dependence on time, but agrees with the evolution of V along PDE solutions. Right? First of all, notice that this is not an integral functional. In the quadratic case, this was an integral functional. But now, right, each A is a integration of your solution, your unknown solution U against a particular mode. So each A is an integral, and I have a polynomial function of integrals. So this is more complicated. Nonetheless, this is a variational problem. It's just not an integral variational problem. And if I could evaluate it, I could decide whether or not V must decrease monotonically for all admissible perturbations. However, this is intractable as written. But I'm going to try to express this right-hand side not in terms of the full tail V, but I'm trying to estimate it in terms of just the energy of the tail, right? So I want to estimate the V-dependent quantities in the boxed expression in terms of just the amplitudes of this finite number of modes that I'm including in my partial Galerkin expansion, as well as the energy of the tail. Right? And first of all, this becomes easier if the basis that I choose is the eigenbasis of the energy stability operator. So this energy analysis, it doesn't go away. It just becomes a component of this generalization. In particular, this gives us a very simple estimate of this gamma term in terms of the energy of the tail of the perturbation, where lambda n plus 1 is the first eigenvalue that I haven't included in my partial Galerkin expansion, and that should be negative. Okay, and then I'm not going to go into details of how this is done, but this middle term, in a fairly technical way, I'm able to come up with a polynomial C that depends explicitly on the finite number of mode amplitudes as well as the energy of the tail that is guaranteed to be an upper bound on this middle term. So what I've now done using these pieces is I've ended up with a polynomial expression Q, which I can consider now as a function on just Rn plus 1 because it does not depend on the tail, just the energy of the tail, right? So a sufficient condition for the time derivative of V to be less than or equal to 0 is for this supremum of this polynomial expression to be less than or equal to 0. Right? In other words, I have V being a sum of squares polynomial. I'm going to require negative Q to be a sum of squares polynomial. I've swept under the rug that there are some additional sum of squares constraints that ensure that Q really is an upper bound on the functional that's equal to the time evolution of V. Right? But I will tell you, even though I haven't written all these things out explicitly, that the tunable polynomial V, right, its coefficients appear linearly in all of these expressions. Thus, this is a sum of squares program. It's convex. A computer can, for a specified class of polynomials in which I seek V, the computer will definitively tell you whether such a V exists, satisfying these constraints or not. If such a V exists, that's your Lyapunov functional for the full Navier-Stokes equations up to numerical error. Okay, so the details of this are pretty technical and I haven't shown them. This paper is still in the publication pipeline, but you can find this archive preprint from a year and a half ago. And this is joint work with Federico Fuentes and Sergei Chernyshenko. So I'm going to apply this to 2D coetflow. So remember, now I want to come up with a non-quadratic Lyapunov functional that is depending explicitly on the projection of the unknown perturbation field onto these energy eigenmodes as I've plotted on the right-hand side, as well as the energy of the part of the unknown perturbation that you're not projecting. So the algorithm is the following. I pick a certain number of eigenmodes that I'm going to use. I fix the domain, I fix the Reynolds number, I compute these eigenmodes. This is semi-analytical, it's almost all doable analytically. Then I build this computational sum of squares program. To do that, I have to do various projections and integrals, but these are all extremely accurate. I then solve this sum of squares program to find coefficients of a polynomial V for which V is guaranteed to be a Lyapunov functional for the full PDE up to numerical error in the solution of the sum of squares program. If this succeeds, I try it at a larger Reynolds number. If it fails, I try it at a smaller Reynolds number. And this is a time-consuming procedure, but what you get out of it in the end is the following. So here, for various choices of the width-to-height ratio of the domain, this black curve is what you get from Orr's classic analysis over 100 years ago. Below this black curve, energy is monotonically decreasing. The energy is a Lyapunov functional, showing that the laminar state is globally attracting. Above this black curve, energy can grow transiently, so previously nothing was known about stability. Okay, but if I carry out the procedure that I described, well, with more and more modes, you do better and better. So let me just say with 13 modes that I'm explicitly letting my Lyapunov functional depend explicitly on the projection of the unknown perturbation onto 13 different modes of the energy stability operator. Right? And if I go to the domain at which Orr's analysis gives a cutoff of 177 as your critical Reynolds number, now it's more like, let's say about 255. So at a Reynolds number of 255, I'm able to construct this complicated quartic function that I can show is a Lyapunov functional for this system. Okay, so this, in summary of the first part of this talk, for nonlinear stability in Navier-Stokes and related equations, using non-quadratic Lyapunov functions is much more technical than the energy method. Here, we showed one particular way of generalizing beyond quadratic Lyapunov functionals, which is to use this partial Goluskin expansion, semi-analytical estimates, projections, and in the end, computational sum of squares programming. Right? However, one of our ongoing goals is to do a different type of generalization that allows us to proceed analytically. In this example that I showed you, 2D coetflow, it gives us moderate improvement of existing global stability results. Right? The energy method showed that you have the laminar state globally stable up to a Reynolds number of 177. Here, for a certain domain size, we increase that number to 250. The correct answer is probably plus infinity. So in that sense, this is a modest improvement. On the other hand, I'm pretty sure that this is the first global stability result for any fluid flow that surpasses the energy method, or slight generalizations of the energy method that also rely on quadratic integral functions. So I think from a methodological standpoint, this is an important proof of concept, and it indicates that in the future, other ways of generalizing beyond quadratic Lyapunov functionals should be explored. I think I'll stop here and ask if there's any quick clarification questions before I go to the second half. Does anyone want to ask anything?
Yeah, I got a question on your, can you go back one slide?
Yes.
So right here, it seems like going from 12 to 13 modes is a dramatic improvement. Well, not dramatic, but is a significant improvement.
Yes.
So what do 14, 15, etc. offer?
I don't know, because the computations become too expensive.
So you stopped at 13 because of expense.
Exactly.
Okay.
Yeah, and then there's the question of which 13 modes do you pick? So one rule of thumb is you want to pick the ones whose eigenvalues are relatively large, but it turned out that just picking the 13 leading eigenvalues was not the optimal thing to do. So yeah, it would not be possible to keep pushing this larger and larger, but on the other hand, in a lot of other fluid systems, there's only a finite gap where the stability is unknown, so you wouldn't have to push this infinitely far.
Okay, thank you.
Okay, so I have only 11 minutes left. I'm going to rush through the second half of this talk because it is very analogous to the first half in mathematical technique, and I hope that it's not too fast for you to get something from it. So right, if you want to bound time averages, it turns out, you might think of some infinite time average in a turbulent system that's of physical interest. So time average turbulent dissipation or drag or lift on an airplane wing, right? All these things are of interest. And beyond a certain Reynolds number, it's intractable to simulate the flow, even on a supercomputer, because the scales become so extreme. So if you want to know, how various time averages scale in the turbulent limit, for example, right, you'd like to compute a priori bounds, especially analytically. But what I'm going to show here again is a computational proof of concept of this method of generalization. So let's say we again have a PDE solution. Maybe it's still Navier-Stokes, and that at each instant in time, there's some class of spatial functions where our solutions live. And we have some quantity of interest, let's say kinetic energy or turbulent drag, that at each instant in time is just a real valued quantity. Well, let's consider the infinite time average of this quantity along a PDE solution. I denote the infinite time average by an overbar. And this in general depends on the initial condition. I mean, even if there's only one attracting state, you still have various unstable traveling waves, periodic orbits, right? And if you start on one of these unstable states, mathematically speaking, you have a different infinite time average. So a well-posed question would be to say, among all trajectories of your system, what is the maximum infinite time average of the quantity that you're interested in, right? So then one tries to derive a priori bounds on this without actually solving the PDE, which generally is not possible. And in particular, this can be done similar to the Lyapunov approach, right? Where I look for some real valued functional V, except the conditions I'm going to put on V are a bit different than the conditions on a Lyapunov functional. In particular, I'm going to require that V is something that I know to be bounded forward in time. For instance, if V is just the L2 energy in many configurations of Navier-Stokes, it's possible to show that the L2 norm remains bounded forward in time, even if you don't know that you have well-posedness, because this would require boundedness of a different norm. So the functional LV, right, this is this Lie derivative of V along solutions, right? LV is just this functional that has the property of agreeing with the time derivative of V along PDE solutions. And its infinite time average along solutions is 0. Right? It's not hard to show that if you have a quantity that's bounded forward in time, the infinite time average of its time derivative must vanish. Why is this useful? Well, the infinite time average of some quantity phi that we're interested in will be the same as the infinite time average of phi plus the Lie derivative of any bounded functional V, right? And I don't know how to take this time average because I don't know the trajectories. But if I simply forget about the time average and treat this phi plus LV as a functional of spatial functions U, then I can just ask for the supremum, right? And that's a variational problem. Once again, a variational problem has arisen in the analysis of this PDE. Why is this even a good idea? Well, suppose phi was just the energy, the L2 energy, and I had V equals 0. Well, the supremum of phi would just be plus infinity for all admissible solutions to the equation, so that's not useful. But for a clever choice of V, it can become the case that phi plus LV is in fact bounded above, and this can give me a finite a priori bound. In particular, well, everything I've said is true for all trajectories, so I can take the supremum over all trajectories on the left-hand side. But you also might imagine this right-hand upper bound, you want to optimize somehow over the choice of the functional V. So for V within some class, right, you want to somehow solve this min-max variational problem. Well, unless I choose a certain class of V functionals, this is an extremely general situation. For Navier-Stokes type PDEs, what people have traditionally done is chosen V to be a quadratic functional, and this goes by the name of the background method. Now, when showing stability, our only option was for V to be the energy because we couldn't have constant or linear terms. Here, there's some benefit to having a linear term as well, right? So the background method has typically been, well, actually it hasn't been written in this way. The fact that there exists such a functional V has sort of been implicit in most of the analysis in the past. But what is described as the background method in the literature is exactly equivalent to choosing a V of this form, where zeta is a known function. And I wrote that zeta is continuous, but it actually has to have one or two derivatives as well. So in other words, U is your unknown PDE solution, but zeta is a chosen function. Energy, and essentially because it's the inner product of u with some function zeta. The constant is irrelevant because hopefully you understood previously why the quadratic term had to be the energy, right? Because I need it when I take a time derivative, I need. Can you still hear me? I just got a message that my internet is unstable.
You were a little bit choppy for a few minutes, but for a half a minute, but you're good now. I'm not sure if you know if you heard what I said.
Okay. I'm going to switch networks. I'm going to skip all the mathematics. Given that I don't have much time left and that the internet just cut out, I think I'm not going to try to explain the mathematics of this part. I'm just going to skip to the results, but I'm going to show you, or let me tell you that essentially what I did was I generalized this V functional beyond the quadratic case, analogously to what was done in the fluid stability problem by considering its dependence on amplitudes of projections onto a finite number of chosen modes and the energy of the tail of the projection. And I'm going to just tell you that for the Kuramoto-Sivashinsky equation, which is the example that I'd like to use here, in 1D, which has a Navier-Stokes type nonlinearity, there is the parameter in this problem is the domain size, which here I've called 2 pi L. And there's a question about how the spatially averaged L2 energy of solutions depends on the domain size, in particular, whether it remains order 1 as the domain size goes to infinity. So I'm going to skip a lot. Okay. So this is a partial bifurcation diagram for the Kuramoto-Sivashinsky equation. The zero solution is globally attracting when L is less than 1. At each integer value of L, there bifurcates a steady state that's shown here. And in fact, essentially the same steady state with different copies of it in the domain bifurcates at every integer value of L. Here I'm showing you this bifurcation diagram on a log-log plot with the spatially averaged energy as a function of the domain size L. And if you do sort of the classic background method thing and use a quadratic functional to get a variational problem whose solution gives you an a priori upper bound on the spatially averaged energy, you get what's shown in blue here. Each one of these dots, I fix the domain size, I solve the variational problem numerically. This previously has been done analytically. Because I skipped slides, I skipped the fact that there's a history on this. Going back to Nikolenko, Scherer, and Tamam in '85, Bronsky and Gamble in 2006. Right? And essentially, this variational type analysis of constructing these V functionals is exhausted for quadratic functionals by this upper bound. But by going to degree 4 or degree 6 functionals, analogously to what I described in the fluid stability case, right, and eventually solving a sum of squares optimization problem numerically, I'm able to construct functionals V that imply upper bounds given by these black dots. And let me just zoom in here. And you can see that these upper bounds, in fact, to numerical error, sit exactly on these known nonlinear steady states. So this implies not only is the energy remaining order 1, but the maximum spatially averaged energy is attained by these simplest steady states. And then the bound diverges. But if I go to a more complicated V function, I end up with a degree 6 bound. And then after a while, I stop computing because it's getting more and more expensive. So computationally going to L to infinity is not realistic. So instead, I'll just end with some speculation, which is that in this equation, I think it's probably actually the steady states that maximize the time averaged energy, but that using my approach as L goes to infinity, sharp bounds require the polynomial degree of your V functionals to go higher, This gives you increasing computational complexity that eventually becomes intractable. But again, it's a proof of concept that this generalization gives stronger results. And the way I generalize, although it leads to expensive computations, is not the only way in which one can try to generalize these type of variational approaches. So I think the clear open question is there a relatively simple functional V that is suboptimal but gives the optimal scaling that's conjectured for these bounds as L goes to infinity? So I will stop there and just say that these are the references in which these methods that I've described can be found. The first half was joint work with Federico Fuentes and Sergei Chernyshenko. The second half that I largely skipped over was joint work with Giovanni Fantuzzi. Thank you for your time.